Hello everyone and welcome to my talk on observing single atom catalytic sites during reactions using electrospray ionization mass spectrometry. My name is Max and I'm a last year PhD student at the National University of Singapore. Single atom catalysts are the ultimate dispersion of noble metals on supports. When going from the bulk to nano and sub-nano structured materials, we end up with the ultimate dispersion of metals on supports. Single atom catalysts are also the bridge between heterogeneous catalysis and homogeneous catalysis, combining the best of both worlds. Here I will discuss with you how a tool that is usually applied to homogeneous catalysts can be applied to heterogeneous catalysts as well. Polyoxymetallates are small, molecularly defined metal oxoclusters. There's a variety of structures as shown here, but I will be, in my talk, mostly focusing on this Kagan structure that is also shown on the left here. The composition is H3PW12O40, or we'll be using a lacunary POM. Composition of that is PW11O39. Electrospray ionization mass spectrometry, of short ESI-MS, is an ideal tool for the elucidation of homogeneously catalyzed reactions. During the ESI-MS, we take a solution out of a reaction flask where certain catalytic reactions with different intermediates is happening. This solution will then be sprayed into an ionization chamber. The solvent will be removed and the naked ions will go into the mass filter. After this mass filter, we can either directly detect the ions or we can go through a collision cell. In this collision cell, by collision with argon ions, we can induce fragmentation of different molecular species, which can then be again mass filtered and detected separately. By this, we can separate the spectra of different intermediates and get information on each of those intermediates individually. And we can even see the gas phase reactivity of each of those intermediates by fragmentation. The active site formation is done in situ. So if we have a flask like this and we use a molar ratio of 1:1 of our polyoxymetallate, PW11O39, and for example, a rhodium salt in a 1:1 ratio, we see the formation of the active site in situ. In black on the bottom here is the polyoxymetallate itself. There's a lot of peaks here because for each of those highly charged species, there will be some cations associating with it, so that the total charge reaches 3- in this particular M/Z ratio. The values for X, Y, and Z in this kind of matrix form here indicates the amount of protons, sodium, and potassium cations that are associated with PW11O39. This gives rise to a fairly complex cation envelope. Once we bind rhodium 3+ ions to the PW11, we only get 3 discernible peaks, one containing a proton, sodium, and potassium cation. Now, through this solution of active site of catalyst, we can bubble different gases. So if we bubble, for example, carbon monoxide containing gas atmosphere for 2 minutes, we see a formation of different catalyst intermediates. In this case, it's carbon monoxide bound to rhodium 3+. If we bubble carbon monoxide for long enough, for 1 hour, then we actually see that rhodium becomes reduced from rhodium 3+ to rhodium 1+, and the PW11O39 now lost 1 oxygen atom and becomes an oxygen vacant PW11O38 species. The big benefit of ESI-MS is that we can get the exact reaction stoichiometry, the stoichiometry of each of the intermediates during reactions. Now, after a treatment with 1 hour carbon monoxide, we treat the solution for 1 hour with an oxygen-containing atmosphere. We again see a change in the mass spectra, which are consistent with the formation of a catalyst intermediate containing dioxygen as well. Now, as I mentioned earlier, we can also do fragmentation of each of those intermediates. If, for example, we take this intermediate with 2 carbon monoxide molecules bound to rhodium, and one of the carbon monoxide molecules already bound to the oxygen of the polyoxymetallate, then we can have different gas phase reactions. One of those, for example, is the desorption of carbon monoxide, as indicated by going from this peak to this mass peak here. On the other hand, we can also have the formation of carbon dioxide. So this carbon monoxide molecule here takes 1 oxygen atom from the polyoxymetallate, forms a carbon dioxide, and this carbon dioxide is desorbed, giving rise to this mass peak here. We're following the same kind of logic. This is the state before the second CO oxidation in the whole reaction cycle. I will show you in a bit. We can again, if we fragment this intermediate, we can either lead to the desorption of both carbon monoxide molecules, or we can again form carbon dioxide, cleaving the dioxygen that is bound into the vacancy, and reforming the PW11039. This all becomes a bit clearer if we look at the whole reaction sequence. First of all, we start with the rhodium single atom catalyst with 2 carbon monoxide molecules bound to it. This is in a hexagonal shape and is a rhodium 3+ species. Upon the removal of carbon dioxide and the oxygen vacancy formation in the polyoxymetallate, rhodium is reduced to rhodium 1+ and now forms a kind of tetragonal planar species. Upon the reabsorption of carbon monoxide, this will bind on the side where the oxygen vacancy just formed. Based on DFT calculations, we see that there's a rearrangement of this structure into this tetragonal structure again. After this, we have the adsorption of a dioxygen molecule into the oxygen vacancy here, which then, upon cleavage of this dioxygen molecule, can go back to this rhodium structure bound to 5 oxygen atoms, 4 on each of the sides here, and 1 on the bottom, as well as 1 carbon monoxide molecule, which then again, upon absorption of carbon monoxide, will reform into this active site structure as we've shown in the beginning. Each of those intermediates, except A2, were observed by ESI-MS, and we also did DFT calculations confirming the stability of each of the intermediates, as well as the relatively low transition state energies in between each of those intermediates. Those calculations were done on the highly charged PW11039 rhodium 1, and in total a charge of 4- active site. We found, based on experiments, that the CO oxidation, that is this step here between A5 and A6, is the rate determining step. This is not entirely consistent with the DFT calculations, which suggest that the step before this, the oxygen adsorption, has the highest transition state energy. This is very well in accordance with what we have observed previously based on in situ spectroscopy on a truly heterogeneous single atom catalyst, which we reported a bit earlier, where we found as well that the adsorption of dioxygen, or the refill of the oxygen vacancy by dioxygen, is rate determining. If we calculate the whole reaction cycle based on a neutral protonated active site structure, that is the composition of H4 PW11039 rhodium 1, then we see that overall it follows the exact same reaction pathway. There's just one big difference, and that is that this step that was previously rate determining based on DFT calculations now essentially can happen without any noticeable barrier, while the step after this, that is the reoxidation of the polyoxymetallate, now becomes rate determining, which is in great accordance with our experimental data. After we've shown this this methodology to work for the rhodium zinc atom catalyzed CO oxidation in the liquid phase. We also were interested in the liquid phase oxidation of benzyl alcohol. For this, we've used a different zinc atom catalyst, that is PW11O39 iron 1, which we found to be the most active for this conversion in our case. If we expose our zinc atom catalyst to a mixture of hydrogen peroxide and benzyl alcohol in an aqueous environment, what we find is a mixture of different intermediates, which, upon careful delineation, we can assign to 3 different intermediates. One is actually the product-bound, benzaldehyde-bound single atom catalyst state, the final state. One is the iron oxo, the highly charged iron oxo species, and one is the hydroperoxo intermediate. We can again use fragmentation to first confirm the composition of the intermediate, as well as the gas phase reactivity of different intermediates. On the left here is the iron oxo intermediate, whereas on the right there's the iron hydroperoxo intermediate, the one that is indicated in purple here. We can run the benzyl alcohol oxidation at different temperatures, and when we draw sample at those temperatures and within half a minute we can do the analysis, then we can actually get the temperature-dependent concentration of each of those intermediates, which then allows us to plot Arrhenius plots for each of those intermediates individually. This allows us to get the reaction barriers for each of those intermediates. For example, we found that the reaction barrier is 121 kilojoule per mole for the reaction after the iron hydroperoxo intermediate. Altogether, we can figure out the reaction mechanism for the benzyl alcohol oxidation on PW11O39 iron 1. Those data are completely obtained by ESI-MS, and we found that there is an iron hydroperoxo intermediate followed by the iron 5+ oxo species, which then can oxidize the benzyl alcohol to benzaldehyde, which then desorbs benzyl alcohol, adsorbs again onto the active site, and the reaction cycle is closed. We also found that the hydroperoxo, the transformation of the hydroperoxo species into the iron oxo species is the rate-determining step of the whole reaction cycle. In conclusion, I hope I could convince you that we are able to get a lot of active site information by ESI-MS, that this approach is applicable for both gas and liquid phase reactions and is not dependent on one particular kind of catalyst. Although for now, we have to resort to some soluble model metal oxide species. There's a great synergy with DFT calculations, since we know the exact stoichiometry and we get some idea about the binding pattern based on the fragmentation of each of those intermediates. Kinetic ESI-MS can reveal activation barriers for between each of those intermediates. With that, I would like to acknowledge my group at NUS. The group at NUS, the Green Catalysis Lab, Professor Ning Yan, my supervisor for the last 4 years, as well as our collaborators from the University of California, LA, which is Professor Philip Sauté and Dr. Sun Gao. Thank you for your attention, and I hope we can have a discussion later on.